Nenomatica, where mathematics meets YouTube excellence. In this example, we find the largest value of lambda, so that an inequality holds for every positive a. We'll build intuition visually and prove the result step by step. Here is the example and the exact inequality we must analyze. Quick challenge. Before we begin, can you guess a substitution that simplifies both sides at once? Step 1. Substitute t equals a plus 1 over a and record its key property. Step 2. Factor the numerator as a product with t minus 2. This reveals a clean comparison function. To see the minimum clearly, we sketch the curve y equals parentheses t plus 1 close parentheses squared for t at least 2 and mark its lowest point. Step 3. Reduce the inequality to a product and deduce the requirement on lambda. Step 4. Minimize parentheses, t plus 1 close parentheses squared on t greater or equal to. The minimum occurs at t equals 2 and equals 9. Therefore, the largest lambda is 9. Answer: the largest value of lambda that works for all positive a is 9. Quick recap. Substitute t equals a plus 1 over a factor. In this lesson, we will find the largest possible value of lambda, such that for every positive a, the inequality holds a cubed plus 1 over a cubed minus 2 is at least lambda times the quantity a plus 1 over a minus 2. We will rewrite the left side to match a well-known identity, and then use the AMGM inequality to bound the right side. Step 1. We will rewrite the left side, so it fits the identity for a cubed plus b cubed plus c cubed minus 3abc. Notice, a cubed plus 1 over a cubed minus 2 can be written as a cubed plus 1 over a cubed plus negative 2 cubed minus 3 times a times 1 over a times negative 2. This is exactly the left side of the identity with a equal to a, b equal to 1 over a, and c equal to negative 2. Step 2. Substitute a equals a, b equals 1 over a, and c equals negative 2 into the identity. Then the product becomes a plus 1 over a minus 2 times the bracket a squared plus 1 over a squared plus 4 minus a times 1 over minus bc minus ac. Be careful with the signs, because c is negative 2, minus bc becomes plus 2 over a, and minus ac becomes plus 2a. So the left side equals the factor a plus 1 over a minus 2 times the bracket a squared plus 1 over a squared plus 3 plus 2 times the quantity a plus 1 over a. Step 3. The factor a plus 1 over a minus 2 is always non-negative for positive a by AMGM, because a plus 1 over a is at least 2 with equality at a equals 1. Therefore, for all positive a, we can compare the two sides by dividing through by the non-negative factor. We obtain that lambda must be less than or equal to a squared plus 1 over a squared plus 3 plus 2 times the quantity a plus 1 over a. Step 4. To find the largest possible lambda that works for every positive, we need the minimum of the right side. Apply AMGM twice. First, a squared plus 1 over a squared is at least 2. Second, a plus 1 over a is at least 2. So 2 times that sum is at least 4. Therefore, the expression is at least 2 plus 3 plus 4, which is 9. This shows that lambda must be at most 9. In this lesson, we will solve the following optimization problem. Given positive numbers x, y, and n with the condition that open parenthesis x plus 1 close parenthesis times open parenthesis y plus 1 close parenthesis equals 2, and xy plus 1 over x, y is at least n. Find the largest value of n. Step 1. Expand the product. Using the rule left parenthesis a plus b, right parenthesis times left parenthesis c plus d, right parenthesis equals a c plus a d plus bc plus bd. We get xy plus x plus y plus 1 equals 2. Step 2. Isolate the product xy. We move x plus y plus 1 to the right side to get x, y equals 1 minus x minus y. Step 3. Use positivity. Since x and y are positive, their product x, y is positive. Therefore, 1 minus x minus y equals xy is greater than 0. Step 4. Substitute x, y equals 1 minus x minus y into the inequality. We obtain 1 minus x minus y plus 1 over 1 minus x minus y is at least n with the condition that 1 minus x minus y remains positive. Step 5. Multiply both sides by the positive quantity, 1 minus x minus y. We get 1 minus x minus y quantity squared plus 1 is at least n times 1 minus x minus y. Step 6. Expand the square. The quantity 1 minus x minus y squared equals 1 plus x squared plus y squared minus 2x minus 2y plus 2xy. So the inequality becomes 1 plus x squared plus y squared minus 2x minus 2y plus 2xy plus 1 is at least n times 1 minus x minus y. Step 7. Group terms for clarity. Put x squared plus y squared plus 2xy together, and group the rest as twice the quantity 1 minus x minus y. Step 8. Replace the expression 1 minus x minus y with xy again. This gives x squared plus y squared plus 2x, y plus 2x, y is at least n times xy. Step 9. Combine like terms. We get x squared plus y squared plus 4x, y is at least n times xy. Step 10. Rearrange to isolate the left side. This becomes x squared plus y squared is at least xy times the quantity n minus 4. The maximum value of n that makes the inequality true is 6. This is the rule we will aim to justify and reach exactly n less than or equal to 6. Step 2. We use the equality case of the inequality x squared plus y squared is greater than or equal to 2xy, which occurs when x equals y. Together with the condition open parenthesis x plus 1 close parenthesis times open parenthesis y plus 1 close parenthesis equals 2, we set x equal y. Then open parenthesis x plus 1 close parenthesis times open parenthesis x plus 1 close parenthesis equals 2. Step 3. Take the square root of both sides. We get open parenthesis x plus 1 close parenthesis squared equals 2. So x plus 1 equals square root of 2. We will use the principal square root. Step 4. Isolate x. From x plus 1 equals square root 2, we get x equals square root 2 minus 1. Since x equals y, we also have x equals y. Step 5. Conclude the value for y. Because x equals y, we have y equals square root 2 minus 1. So the pair is x equals y equals square root 2 minus 1. Example. Find the largest real number k such that for all real a, b, and c, the quantity open parenthesis, a plus b plus c close parenthesis squared times open parenthesis, ab plus bc plus c, a close parenthesis is greater than or equal to k times open parenthesis, a squared b squared plus b squared c squared plus c squared a squared close parenthesis. Step 1. Use the non-negativity of a square. The square root of a minus the square root of b, all squared, is greater than or equal to 0. Expanding, a minus 2 times the square root of ab plus b is greater than or equal to 0, which implies a plus b is greater than or equal to 2 times the square root of ab. Step 2. Compare the sum of 3 to the sum of 2. We have open parenthesis, a plus b plus c, close parenthesis squared, is greater than or equal to open parenthesis, a plus b close parenthesis squared. Using step 1, a plus b is at least 2 times the square root of ab. So open parenthesis, a plus b close parenthesis squared is at least 4ab. Therefore, open parenthesis, a plus b plus c close parenthesis squared is at least 4ab. Step 3, multiply by ab, which is non-negative when we apply the square root form. We get open parenthesis, a plus b plus c close parenthesis squared times ab is greater than or equal to 4 squared b squared. Step 4. Write the analogous statements for the other pairs. Similarly, open parenthesis, a plus b plus c close parenthesis squared times bc is at least 4b squared c squared, and open parenthesis, a plus b plus c close parenthesis squared times c a is at least 4c squared a squared. Step 5. Add the 3 inequalities together. On the left, we factor out open parenthesis, a plus b plus c close parenthesis squared times open parenthesis, ab plus bc plus c a close parenthesis. On the right, we get 4 times the sum of a squared b squared c squared, and c squared a squared. So the inequality holds with k equal to 4. Celebration. The largest value of k is 4. In this video, we will find the minimum value of the expression 2x squared plus 2x, y plus 4, y plus 5y squared minus x. We will complete the square to rewrite it as a sum of squares, and then use the fact that squares are always non-negative. Step 1. Rewrite the expression by completing the square. Here is the completed form as a sum of 3 perfect squares minus a constant. We will color code each square to make it clear. To see why this works, each colored term expands to parts of the original expression. We will briefly expand and combine like terms to match the original expression. Step 2. The minimum of a sum of squares occurs when each square is 0. Since squares can never be negative, the whole expression is at least -5/4. The minimum happens when all 3 squares are 0, x minus 1/2 equals 0, x plus y equals 0, and 2y plus 1 equals 0. From x minus 1/2 equals 0, we get x equals 1/2. From 2y plus 1 equals 0, we get y equals -1/2. Notice that x plus y equals 0 is automatically satisfied by these values. Therefore, the minimum value is -5/4, achieved at x equals 1/2 and y equals -1/2. Let's work through a clean inequality example about the symmetric sum ab plus bc plus ca. We'll present each step with a rule box and highlight the changing pieces in orange. Here is the example statement. Quick challenge. Can you predict the upper bound for S before we derive it? Step 1. We use the rule that the sum of squares of differences is non-negative. Then expand. Substitute a squared plus b squared plus c squared equals 1, and isolate S. Notice the orange highlights mark what changed from the previous line. Pause and reflect. Why must the lower bound be at least -1/2? Step 2. We use the rule that the square of a sum is non-negative. Expand. Substitute 1 for a squared plus b squared plus c squared, and solve the inequality for S. Again, the orange highlight marks the new changed part. And we are done. The range for S is from -1/2 up to 1 inclusive. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.